Okay, let's go back to this picture again. Here, this red loop is just a hypothetical loop. It doesn't exist. It's just a mathematical imagination. Now, in a sense, you can think of it also in this form. You see, there is an area bounded by that loop. And just like when we were discussing the flux, electric flux in the Gauss's law, when there is an area, we had to define the positive and negative side of that area, negative sense of that area. Here, we also need to define the inside and outside of this area. And the way we define the inside this area and outside this area is the right-hand rule. So here, this is the area. Since we chose the loop to be moving in the counterclockwise sense, the positive outside of this area is towards you. So this loop over here is entering from the outside and going to the inside. So that is why we call this negative. It's going inside. This one is from inside to outside. That is why we define it to be positive. And if you had, I don't know, some other loop which doesn't touch this screen but just go like this, well, it doesn't go from outside to inside, neither from inside to outside, so it doesn't contribute. So the only contributions from these to that integral will be from the currents that pass through this area. They have to pass through that area. And if they are going from inside to outside, they will contribute positively. And if they are going from outside to inside, they will contribute negatively, independent of what angle they make with this area. Now let's do an application of this. So let's calculate the magnetic field created by a thick loop, thick wire. It's not infinitely thin. So what we have over here, we have this wire that is infinitely long. And it carries a total current I. It has a radius, let's call it R. And we will assume that I is, for example, uniformly distributed. So if I just imagine a very small area, over there, the current running through that area will be I times that area over pi r squared. I over pi r squared is the current per area. So if I multiply it by the area, I obtain the total current passing through that area. That's what I mean when I say that the current is uniformly distributed. Now, rather than showing it in this form, let us look at it straight from one side. This is my wire, radius R. The current, let's say, is going into the screen. So the wire starts from there at infinity. It goes straight and goes up to the infinity over there. I'm just looking at the cross-section of the wire. And I will use the Ampere's law to calculate the magnetic field both inside the wire and outside the wire. Now, the steps to use the Ampere's law is, in fact, exactly the same as the steps that we use to use the Gauss law. First, we have to say something about the magnetic field. You see, we want to use this equation to calculate the magnetic field. But without knowing something about the magnetic field, I cannot evaluate this integral, and hence I cannot use it. So the first thing I have to determine is, what does the magnetic field look like? So, for example, the magnetic field, let's say at this point, do you expect that magnetic field to be different than the magnetic field at this point? Why not? It's the same. If I just shift this wire along its axis, nothing changes. But this point becomes this point if I shift it along the wire. So this point and this point should have the same magnetic field. So if I would just define my axis, x, y, and z. One thing, the magnetic field cannot depend on z, because nothing changes as I shift my wire along the z-axis, along its axis. Nothing changes, so the magnetic field should not change. So the magnetic field cannot depend on z. Now, what other thing doesn't change the magnetic field? Or what other transformations that we can imagine doesn't change the current? Because if the current doesn't change, the magnetic field doesn't change. If I rotate my cylinder around its axis, does anything change? Well, nothing changes. The current doesn't change. The wire doesn't change. Nothing changes. So the magnetic field also should not change. So the magnetic field should also be independent of these rotations. But that basically tells me that the magnetic field can only depend on the distance from the central axis. So if this is the central axis of the wire, and if I'm looking at the magnetic field at some point over here, at least the magnitude can only depend on that distance. Let me call that distance rho. The magnitude of the magnetic field is a function of that distance only and nothing else. It cannot depend on z. It cannot depend on the angle. The only thing it can depend on is rho. Now, what about its direction? Now, in the case of we had also studied a similar problem when we were using the Gauss law. You see, we had this cylinder, uniformly charged cylinder problem. There we said that the electric field should be radially outward, because there the electric field had to start from a given point. It had to start from a given point and it had to go radially outward. But here, the magnetic field cannot start from a given point. It just cannot start from any point. So it cannot start from any point, the magnetic field. It shouldn't change if I just shifted this wire, or it shouldn't look any different if I just move along the wire. It should be the same, because the wire looks the same. As if I rotate the wire, it also shouldn't change. The only possible way is that the magnetic field lines should be just circles. So the magnetic field itself its magnitude is a function of rho only. Well, let me just show that circular direction to be the direction in which the phi angle increases. Are you familiar with that notation? Phi hat. Yeah. You see, if I look at it from this direction, you see, this is what I had. So at this point, let's say again, right-hand rule, if the z is going into the screen, so phi hat, at that point, this is the phi hat. At this point, this is phi hat. At this point, this is phi hat. That is the direction of phi hat. So it changes from point to point, and it just circles the z-axis. Now let's calculate the magnetic field. Now we already know something about the magnetic field itself. We know a lot about the magnetic field itself. Now I have to find, to use the Ampere's law, first I have to find the closed loop along which, well, the magnitude is 0. No, not the magnitude is constant. what is that loop? You see, the magnitude depends only on rho. So if I want to find a closed loop along which the magnetic field magnitude is constant, rho should be constant along that loop. So what is the rho is equal to constant loop? It's just a circle. Let me imagine such a circle. Now, which way would you like to go? Clockwise or counterclockwise? Clockwise. Let's go counterclockwise. Why not? It's arbitrary. So let's go around the loop in the counterclockwise sense. Now, first I need to calculate, let me start with calculating B dot dl. Well, what is dl? I just imagine a very small segment. This is my dl. Here is the very small segment. dl vector just points from here to here in that direction. So dl vector is minus dl, or let's say its magnitude, dl, what's pointing at this point, the phi hat vector would be pointing in this direction, but dl points in the opposite direction. So it's dl in the minus phi hat direction. This is my dl vector. Well, my magnetic field, I already know that B is B of rho in the phi hat direction. Well, let me just calculate their scalar product. B dot dl is just B rho in the phi hat direction times minus dl in the phi hat direction. Well, B rho times minus dl. What is phi hat scalar product with phi hat? Remember, it's a unit vector. Just 1. So this is it. This is B dot dl. Well, let me calculate the integral now. Around that loop is minus B rho times dl. Well, now B rho is constant because around the loop I chose, rho is constant. So I can take B rho out of the integral. Minus B rho. dl was the length of that very small segment I chose. Now I'm just summing the length of all those segments, but that gives me the total circumference. Okay, so the left-hand side of Ampere's law we had already calculated. Now, what is the enclosed current? You see, I is distributed uniformly around the cross section. Some of that current I is running through here, which is not inside my loop. I over pi r squared. This is the current density. That is the current running per unit area. The total area inside my loop is pi rho squared. Now, is it positive or negative? The current is running into the screen. Well, my loop is going counterclockwise. Use your right hand. Positive current should be running out of the screen. So this current is negative. So now Ampere's law tells me that minus b rho times 2 pi rho, this is nothing but the b dot dl integral around the loop that I chose. This should be equal to mu 0 times the enclosed current by the loop. It is this one. Minus I over pi r squared times pi rho squared. Now let me also note that this is true only if rho is less than r. Otherwise it won't be true. Now let's do the simplifications. This pi cancels this pi over here. This rho will cancel this rho. One of them, the minuses will cancel. B of rho would be just mu 0 over 2 pi times I rho over r squared. So this is the magnetic field inside the wire. You see, it doesn't decrease as a function of rho because more current is contributing to the wire as we go from the center away from the central axis. So just like in the case of the electric field, if you had a spherical charge distribution, inside this spherical charge distribution, the electric field was 0 if you have just a shell. Here, if you have a cylindrical shell and the current is uniformly distributed over the cylinder, inside the created magnetic field will be 0. So that is why we have this increase as a function of rho, where until rho becomes equal to r, because I enclosed is equal to this one, this expression, only if rho is less than r. So this is correct if rho is less than r. Well, what happens if rho is larger than r? Well, you see, if rho is larger than r, then the enclosed current is the enclosed, that is the enclosed current passing through a disk which has a radius rho inside. If rho is larger than the radius of my wire, then all the current is passing and it just doesn't change. I enclosed would be just minus I, and B rho will be just mu 0 over 2 pi I over r. It's just as if it is just an infinite straight thin wire. Just like if you have a spherical charge distribution, outside the charge distribution it just behaves like a point charge. Here, if you have a cylindrical symmetric current density, outside the cylinder it just behaves like an infinitely thin straight wire. And well, what's the vectorial form? That is the vectorial form of the B. So B is mu 0 over 2 pi. It's always in the phi hat direction times I, no, here I over rho, sorry. I times rho over r squared if rho is less than r, and just 1 over rho if rho is larger than r. This is our magnetic field created by this wire. Any questions here? Suppose we have a ring, a current carrying ring. So this is just this is from an angled view. This is just a cross section. So the current comes towards you and goes away. So the current just turns around the loop in this sense. How do you think will the magnetic field lines look like? Well, let's see, very close to this one, it will rotate counterclockwise. So very close to this one, this will be the direction of the magnetic field lines. Very close to here, it will rotate clockwise. Very close to this part. And as you go towards the center, they will no longer be centered around the wire, but they will still look somewhat circular. So this is how the magnetic field lines of a ring will look like. So it's this ring over here. Now let's imagine we put two rings. We have two rings. So here there is a ring with the current running in this sense. Here there is another ring with the current running towards you in the top and away from you at the bottom. So how do you think the magnetic field lines will look like this time? Well, very close to the wire, they will still be somewhat circular. But as you go away from the wires, well, there will be some magnetic field line coming from here. Well, it will somewhat try to go out from in between, but then it will continue along through the second loop. So this is how it will look like, more or less. So this is how they will look like. You see, this current carrying loop, single loop, is just like a magnet, a very short magnet. Now here we put two very short magnets. So what the magnetic field lines does in this case is it enters the north pole of one of the magnets and leaves from it enters from the south pole, leaves at the north pole, and then since there's another magnet very nearby, it just enters its south pole and leaves its north pole. Well, let's imagine a third one. Well, again, very close to these loops. In between, you will get some circular magnetic field lines. But then there will be other magnetic field lines entering from the south pole of the first magnet, then exiting from its north pole, coming in the south pole of the second magnet, exiting from the north pole, entering the third magnet from the south pole and exiting from the its north pole. So this is more or less how they will look like. Well, how can we reduce these bumps? Bring them together. So if we just bring them together, and we see these bumps appear only in between the wires. If we bring them together, the bumps will be less. And Well, just put many of them, one after the other one. So you will get a long system. Let's see, you will have many wires, many loops, let's say, one after the other one. Ideally infinitely long, and the wires are very thin and very nearby. Ideally, they are just touching each other, let's say. And so since there is no space between the wires, there won't be such bumps. Magnetic field lines will enter from one end, and they will just go straight and exit from the other end. And hypothetically, these ends, you can just imagine them going to infinity. So inside, you get a uniform magnetic field. So you get this uniform magnetic field inside. This is, and zero magnetic field outside. You see, because the magnetic fields cannot escape. They enter from infinity, and they just go to infinity. There's no magnetic field line passing through this point. Now, this is what is called a solenoid. Solenoid. Well, how do you create this? Well, basically, you just get a tube, a non-conducting tube. Well, this is how you make an electromagnet if you just choose a finite length tube. And around this tube, you just wrap your wire. And send a current through it. Of course, you don't wrap it with such spacings. You just make sure that they touch each other. Also, you make sure that they are insulated so that you don't create a short circuit. So these are just covered with an insulator. You make these spacings as short as possible, and you just wrap it as many times as you like around the wire. So at the end of the day, when you send the current through it, what will happen is, well, let's see. You will have magnetic field lines leaving from here and entering here. And inside, it will be more or less uniform. But that is nothing but a magnet, this time created by an electric field. That is what's called an electromagnet. Now, how can we calculate the magnetic field of this system? Well, we can just use the Ampere's law. So I have this solenoid. Let me also show my axis, x, y, and z. Now, what is the direction of the magnetic field? I want to use the Ampere's law, so before using the Ampere's law, I have to know something about my magnetic field. So one thing, what is the direction of this magnetic field? It's along the z-axis, so it's the k-axis, k hat. Now, can the magnitude depend on x? Sorry, can the magnitude depend on z? Yeah, because everything is translational symmetric. can it depend on the angle? Well, everything is rotationally symmetric. Nothing changes under rotation, so it also cannot depend on the angle. It might still depend on the distance from the axis. So if I'm looking for a magnetic field over here, that is my rho. If I'm looking for the magnetic field over here, this distance is rho from the central axis. My magnetic field, in principle, can still depend on rho. I don't know whether it depends or not, but I cannot eliminate such a dependence based on the symmetry. Now let's use the Ampere's law. The first thing I have to do is choose a suitable loop. Now this loop should be such that either the magnitude of B should be constant, or the loop should be perpendicular to k hat. So because if the B rho is constant, I can take it out of that integral. If my loop is perpendicular to k hat, then there is no contribution from that segment anyway. So what is a line which has a rho equal to constant? A circle has rho is equal to constant. So essentially I can imagine such a circle. But if I take such a circle, you see dl is always perpendicular to k. So b dot dl would be 0. And so the current passing through that loop will be 0. It will be still correct. I will have 0 equal to 0, but it won't be useful for me. So I want to find a rho is equal to constant, but at the same time my path should be in the direction of k. That is just a straight line segment. Let's say this line segment. Well, I have to construct a closed loop. Now I have to close that loop to a loop. What I will do is I will add a path segment which is perpendicular to k. Well, I will just add this one. It is perpendicular to k over here. Outside there is no magnetic field. Now I can just go back. Since there is no magnetic field, let's just imagine any path. And here I will just choose close my path by a perpendicular segment again. So this is my closed loop. And this length over here, let's call it L. Any questions on why I choose that loop? You see, this I already determined. Now I will be calculating B dot dl around the closed loop. But if I want to calculate this B dot dl around the loop, I should be able to take this unknown function out of my integral. That is the key point. By choosing such a loop, you see, from this point to this point, B rho is just constant between this point and this point. So I can just take B rho out of the integral. Now from this point to here, B rho is non-zero, but dl is perpendicular to k. Remember, k is in that direction. Along this path, dl is upward. So there is no contribution from this path. Well, from this point up to this point, B is 0. So there is no contribution. From here to here, B is in the k direction, but dl is pointing in this direction. They are perpendicular, no contribution. So the only contribution will be from this point to that point. So if I call the left point A, the right point B, this is just B dot dl from point A to point B. From here to here. Because from here all the way back over here, the contribution is 0. Well, by the way, I had already chosen to go counterclockwise, but it doesn't really matter. You can choose whichever direction you like. So let's see. From A to B, B has that form. This is equal to B rho in the k hat direction. I'm going from A to B, dl vector, no, this dl vector is also in the k direction, in the z direction. So it's just the magnitude times k hat from A to B. So this is just, well, k hat, scalar product with k hat is what? It's 1. B rho is constant from A to B, so I can just take it out. What remains is the sum of the L's, but that gives me the total length from A to B, which is just L. This is the B dot dl integral around that red loop. Now I know to use the Ampere's law, I need to find I enclosed. First of all, the current, is it positive or negative? Well, use your right hand, curl your fingers in the direction of your loop. So this is the positive current. All these currents are in the positive sense. How many of them? Well, I don't know. Let's just call that N. It's N times I. There are N loops within that length L. So N number of loops, current loops. Well, now we have everything. Now, Ampere's law tells me that B rho times L should be equal to N times I times mu 0. So I can find B rho. Mu 0, capital N over L times I. This is B. It doesn't depend on rho. So inside this solenoid, I do have a uniform magnetic field. It's the same everywhere. It's always pointing along the axis of the solenoid. And this N over L is usually denoted by small n. Is the number of turns per unit length. Well, of course, this will be valid only if we have an infinitely long solenoid. If it's not infinitely long, this will not be valid. It will still be a good enough approximation if you have a thin solenoid, a thin but a long one, as long as you are away from the edges. Close to the edges, it will not be valid. Because here we have assumed in our derivation that outside this solenoid, the magnetic field is 0. That is true only if the solenoid is infinitely long. If the solenoid has edges, well, you see the magnetic field lines will leave from the ends of the solenoid and they will just curve to the other side. Well, there's one way to overcome that problem. Well, rather than assuming an infinitely long solenoid, which have some openings, close it up. Bend it to a cylinder, to a circle. So that is what is called a toroid. So here we have, you can just imagine the toroid as you have take a solenoid, just bend it up around. So it just looks like a CIMIT. This is the shape. You just wrap the wire around. And if you just cut it, this is how it will look like. So let's say the current, you send the current such that it gets out of the paper, out of the screen at the top, and it goes into the screen at the bottom. So it's just the current gets out, goes in, gets out, goes in. So it just wraps around your toroid. Well, just like in the previous case, you see in the solenoid, the magnetic field lines went through the axis. In this case also, the magnetic field lines will just go around this toroid. They will make closed circles. Outside, none of them can escape. So everything, all the magnetic field lines will be trapped inside. What will be the direction of the magnetic field lines? Your right-hand rule, well, you can just pick up any of these loops. So take this one, the current is into, so here the magnetic field line is going in that direction. So they will just close the loops in the clockwise sense. This is B. Well, what can we say about the magnetic field line? Magnetic field itself. Well, it goes around the circle. So we can just call that direction the phi direction, just to show the direction. Well, what about the magnitude? Well, in principle, the magnitude can depend on this distance. Well, if you go away from the center, it becomes larger or smaller. Well, and it can also depend on the z component, but it cannot depend on phi. Do you agree? You see, we have this toroid. Close to the center, the magnetic field magnitude can be different than the magnitude away from the center. There is nothing that tells us that they should be the same. Well, if this is my toroid, at the bottom it can have a different magnitude, at the middle it can have a different magnitude, at the top it can have a different magnitude. We don't know yet. In principle, they can all be different. And so it depends on rho, it can depend on z, but it cannot depend on phi, because if I rotate my toroid, nothing changes. My currents are still the same, so the magnetic field should still be the same. And the direction is around that circle. So okay, now we know something about the magnetic field. Now we can use the Ampere's law. First, of course, I have to choose a circle, a closed loop, to evaluate the integral, the loop integral in Ampere's law. So I want to take this out of my loop, out of my integral. So I have to choose a loop around which rho and z are the same, are constant, they don't change. But that's kind of easy, I just assume a circle. Well, in fact, if this is a magnetic field line, I can choose my loop along that magnetic field line. And I can even go in the same direction. Because that magnetic field line has a constant rho and a constant z. That magnetic field line doesn't go up and down around the toroid, it just makes a loop. at constant rho and constant z. So let's see. Now let's use our Ampere's law. B dot dl. Well, you see my dl and b, they are both pointing in the same direction around that loop. So that scalar product is just the product of the magnitudes. But the magnitude of b depends only on rho and z, and my loop has constant rho and constant z. So I can just take the b out. But the sum of that very small segments making my loop just gives me the total circumference of my loop, which is nothing but 2 pi rho. So I had already evaluated this loop integral. And my Ampere's law tells me that this should be equal to mu 0 times I enclosed, which is mu 0 times, let's say, n times I. N is the number of turns of the toroid. Well, you see, my loop goes around all the turns. So if there are n turns, the total current is n times I times mu 0. Is it positive or negative? Well, the loop is going clockwise sense. If you wrap your fingers in the clockwise sense, the positive direction of the current is into the screen. So all the currents inside my loop are going into the screen. So it's positive. So the magnitude of the magnetic field multiplied by 2 pi rho should be equal to mu 0 n times I, which is B of rho z is equal to mu 0 over 2 pi times n times I over rho. So it doesn't depend on z, but it depends on rho. If you are at the edge of this toroid, you see at this point, magnetic field is stronger than it is at this point. So there is a rho dependence. But it doesn't depend on whether you are at the center of the toroid or at the bottom or at the top of the toroid. So you see, at this point, the magnetic field is smaller than at this point, but at this point, the magnetic field is the same as this point. There is no z dependence, but there is a rho dependence. Any questions? So see you on Monday.